Welcome to your 11th Python web scraping tutorial, and in this tutorial we're going to be building a spider algorithm. And basically what a spider algorithm is it creates a queue or a stack of URLs, and then it follows those URLs and it keeps populating more and more URLs and appends them onto the stack. And the only way that you can achieve a spidering algorithm is with a stack or a queue. So a lot of people, when they're web scraping, they know how to retrieve information from one page, but they don't know how to create a data structure that allows them to visit new pages and remember which pages they've already visited. So the libraries we'll be using for this tutorial are URL parse, and basically what that allows us to do is it allows us to view a URL and see if the top level domain is in that URL, and if it's not in that URL we need to append it to the beginning. So a lot of times when you're writing HTML, whenever you have an href or a link to another page, if it's on your same website, you're not going to write HTTP whatever every time. You might just write slash another page, like slash contact.php slash about.html. You're not going to write google.com slash about HTML every single time. So basically what this will do is it will make sure that all of our URLs are formatted the same way with the top level domain included, because we are going to be eventually scraping multiple sites. So let's get started. So first we'll import URL parse. Next we will import URL lib so that we can make network requests and actually view the pages. And we're also going to be using Beautiful Soup. So what Beautiful Soup is it's a library for Python, and if you go to your lib and then you go to a folder called BS4, I couldn't get it to install correctly. So, there's a way in Python that you can get it to automatically put this file here, but I couldn't get that to work, so I ended up just dragging the file. And basically this folder just contains a bunch of compiled Python and some tests. But in order to install a module, you don't really have to do the official way of installing. You can just drag the folder into the lib folder if you're having problems installing it. Okay, so what I've made is I've made a folder called nytimes, and inside is our scrape.py. Because eventually we're going to be getting articles from the New York Times. So next we'll import Beautiful Soup. So we'll say from bs4 import Beautiful Soup. And from bs4 basically means that the folder is named bs4 and the inside is the actual Beautiful Soup code. Next we're going to need basically just what URL are we going to visit. So right now I'll just say URL equals newyorktimes.com, and basically what we need is we need a way to keep track of what URLs we're visiting. We need to visit and which URLs we have already visited. So if we have a stack, we basically need to go to a website, find all of the URLs that we think we want to visit, push all of those onto the stack if they're not already seen in our historical pages that we've already viewed. So if you think about it, what you don't want to do is you do not want to visit any page twice. So we need to keep a running total of the pages that we are interested in searching, and we need to keep a historical record of which pages we've already seen. So I'm going to make two Python lists. So URLs, and basically what I'm going to do is I'm just going to put URL inside there so it has something to start out with. Next, I'll make another one called visited. Visited equals URL as well. So basically, we're going to start out by visiting New York Times, and then we will generate more URLs and push them onto the URL stack. So basically, this is just a stack of URLs to scrape, and this is historic record of URLs. Okay, so next what we're going to do is we're going to have a while loop. And the reason I'm using a while loop is URLs is a list, and it's going to grow and contract. So basically, the way that it will work is it will grow to a certain point, and then it will contract back to 0 as it's running out of leads. So basically, our stack should grow to a certain height. It should grow to some max height, and then it should shrink. And then when the program finishes, the stack will be empty. It has nothing it can do. It has no more leads of where to look for more URLs. So I'm going to say while len of URLs is greater than 0, I'm going to try to open URL of 0. So I'm going to say HTML text equals URL lib.url open and URLs of 0 dot read. And this is actually going to be a queue, because the queue adds to the end and removes from the other side of the list, as opposed to a stack where it both adds and removes from the same end of the list. So if you think of a stack as a stack of plates, you can't pull the plate from the very bottom out. You have to take only from the top, and you have to add plates only to the top. You can't add plates to the middle of the stack or the bottom. But a queue, you think of it like dominoes. You can line them up, you can add them to the front, and you can take them from the back. It's more lenient. So, I mean, both stack and queue are equally helpful to us, but in this case we're using queue. I don't really know. I've never tried to do this with a stack, but it'll probably work reasonably well this way. So, except we don't really want to raise too many errors. We'll just say print URLs of 0, just so we can see which URLs it's getting errors on. I think that the majority of the ones that gets errors will just be it's trying to access like a favicon or something that's not there, or it's accessing a page that has been deleted or something. It will give a URL. I mean, it will give an error. So next, we actually have to use beautiful soup. And what we want to do is convert our HTML text, which is a string of HTML, into a beautiful soup object. Or I think basically beautiful soup is just like a big DOM document, and it's like a big associative array, and you can access certain parts of it. I think that's all the library does. So we'll say soup equals beautiful soup of HTML text. And next we can say urls.pop we want to pop off the first element of our array. because if you look at it, we've loaded the first element of the array. So if we imagine that we have like 3 different things in our array, we load the first one, and then we'll pop that one off, and then the next one will slide down. So the next time we run the loop, it will access the second element, or the second one in the original array. But when we add to the array, we'll add to the end, so it will keep growing on one side and we'll keep removing from one side. So when it's finished, it should be empty. But by adding and removing at the same time, your array will remain at a constant level while it's working, and then eventually it should taper off to 0. So we'll pop off from our URL array, and next we want to find all of the URLs. So we'll say for tag in soup.find all, and the A in the all has to be capitalized for beautiful soup. I'll say we'll find all the A tags, and if you don't know HTML, A is the it's for a URL or a link somewhere. And then href equals true. So basically href equals true just means that it has something in the it has a link. It has somebody has put something inside the quotes of the href tag. So now what we want to do is we want to make sure that our URL is actually part of it's actually including the top level domain. So what I could actually do is instead of saying for tag and soup.findAll, I could just say print soup.findAll this, and we can see what that gives us. So I'll just get rid of these other New York Timeses, and I'm actually going to open up Python. So I'm going to say exec file New York Times /scrape.py, execute our code, and here we can see all of the URLs that it's found. So on the page newyorktimes.com, it has found quite a few URLs. And I could actually say for tag in soup.findAll, I want to say print tag. Okay, so this is finding quite a few URLs, and you can see that most of them have the HTTP, but sometimes it's just slash something. So if I do a different URL, if I go to a site that I own, sparkbrowser.com, I can actually see that some of these URLs, they don't actually have the top level domain, they just have the page of the site. And we actually want to convert this. So we will say tag of href, or we'll just print out tag of href, and that will give us just what's inside the href tag. So as you can see, it didn't include the top level domain, but if I go to New York Times, they probably include it. Okay, so for the New York Times site, you can see we just printed out the href tags, and it got quite a few links. And this is just a big list of all the links that we've found. And next I want to like normalize these URLs. So I'll just say equals URL parse dot URL join. Oh, I thought for a second this had the that keyword already in there. So dot URL join, and then we want to join it to our top level domain. But oh yeah, we have that right there. So we'll say URL plus tag of href. So basically we're just updating tag of href to itself plus the top level domain. And we'll just print these out. So, whoops, print tag. Oh, we can't do a assignment and a print statement in the same statement. So we'll just do that, and then we'll print tag of href. No module has no attribute URL join. URL parse dot URL. Oh, it's URL join, not UR join. So just a simple typing error there. URL join takes at least 2 arguments, 1 given. Oh, it's not plus. It's just a comma there. So it's actually a function that basically combines. I think all the function does is it checks whether it has the top level domain. If it doesn't, it appends it. If it doesn't, it just leaves it be. So basically we could write this function, but whatever, it's already written. Okay, so it looks exactly the same for New York Times because they already normalized their URLs. But if I go back to my website, and I run this for my website, before it was just the homescreen.php, dropbox.php, and now I have the top level domain for each of the links that it's found, which is excellent, because eventually we're going to put this code out onto the web and it's just going to be let loose. So next what we want to do is we want to have an if statement to make sure that the top level domain is in our the URLs we find, because we don't want our code going out onto the internet and going to Twitter and going to Wikipedia, going all over the web, all over the internet. We want it to stay on a certain site. So what we're going to do is we're going to say for each URL we find, I'm going to say if URL in tag of href and tag of href not in visited, we are going to urls.append our tag of href. So let me just copy this. And we're going to also append it to our visited. So visited. Oh, I misspelled visited. That could have caused some problems. I think it's fine now. Dot append tag of href. And at the very end we'll just print out visited. Print visited. Okay, so basically what this will do is it will go out to a website, it will populate, or actually I think a better way to show it would be whenever I pop something off, I will also print the length of URLs. So basically the reason why this works is because URLs has stuff added to it and stuff removed from it with this urls.pop, but visited.append just has stuff added to it. So this is a complete historical record, and this is a temporary stack or queue of jobs that need to be processed. And this is sort of like a scheduling, actually it's nothing like a scheduling algorithm, but I mean it's a spider algorithm, that's what it's for. That's what it's classified as. So let's try it. Okay. So we can see here that 0 is there's 0 elements in the array, and each of these 30, 29, this is how many elements are on the URL's array. So basically what each of these numbers represents is adding another URL to the array, and then as you can see it starts to taper off down to 8, 7, 6, 5 until it gets to 0 and it hasn't found anything. So this is all of the URLs it found for sparkbrowser.com that have something attached to them. So the ones that it got errors for were like sparkbrowser.com, this one here, and let me just try that in the browser and see what it gives us. Okay, so that shouldn't have given us an error, but whatever. So let's try this for another website. So which website should we do it for? Let's try mileycyrus.com. Seems like a reasonable website. Let's enter. And I think that these are all the different pages: backyard sessions, video, merch. So it should find all of these. And this looks like a pretty small website. It doesn't look like it's gonna take 10 million different pages. So let's just replace sparkbrowser.com with mileycyrus.com and then go back to the browser. Actually, I'll just run this first. So Alt-P. Okay, so this is a good example, this website here, because what it does basically is it adds all of the URLs it finds onto the stack. So the first time it ran, the first page, it found, I guess it found another URL, and then it added onto the stack, and then when it was popped from the stack, so it went back to 0, and then I guess it found 5 on the next website, the next page, so then there were 6 on the stack, and then I guess it went to the next page, removed one, and then it went all the way to 0. So we use a stack in order to keep track of which URLs we have to visit in the immediate future, and we use the historical record in order to make sure that we don't visit any pages that we've already visited. And this is a spider algorithm, so I'll just put that at the top, page spider. And you can see what happens if we do this for NewYorkTimes.com, because they have like 10 million pages on their website. So nytimes.com, let's see what happens. Our stack is going to grow pretty big before it starts shrinking. Okay, so our stack is already up to 250 things, and it doesn't look like it's going to be shrinking anytime soon. So what I've found is your stack will grow to a certain point, and then it will start to decrease. And once it starts decreasing, you know you've found like the midpoint, like majority of the pages. But then sometimes it finds a certain page that has like thousands of links on it, and it will just jump up. So I don't think that we're going to be able to spider the entire New York Times website in the extent of this video. So I'll just run it one more time for the kill it. Okay, so New York Times, it's basically has a lot of pages, so our stack is growing pretty large. But I think you get the basic idea of how this works. I placed a lot of emphasis on needing a stack or a queue for a page spider algorithm and needing a historical record. So a bad thing about this is that for every single URL you visit, you have to test it against a historical record. So we're not using any optimization by ordering this record. So what we could do is put this in alphabetical order to make it faster to do a lookup in it. But right now we're just doing them in chronological order. So we have to actually view every single element of this historical record array in order to determine whether we've seen something or not. So that's a pretty good optimization we could do right there. And I'm sure Google has already done that for their page spiders, but this is basically like build it yourself page spider. Just throw it together in 5 minutes, you're done. It's kind of like a backyard project, just like a weekend project here. Just throw it together casual, because we're not Google, so we don't have to, I mean, I guess we could optimize it, but it's good enough for what I'm doing, is explaining in a YouTube video how a page spider algorithm works. So thank you for watching your 11th web scraping tutorial on page spiders.